Hi, welcome to our video. We are going to talk about how to design an earthen dam to protect Thomond village from flooding like it has witnessed in the past. Our team consists of 6 members: Di, Ella, Jack, James, Kevin and myself, Michelle. Hope you enjoy.
The first step of this project was to do a site investigation, which involved digging a trial pit on the site to see what soils we had available to us for the construction of the dam and to build the dam on. Site safety was the number one priority of the site investigation. It was ensured that everyone had adequate PPE, which included a hard hat, high-vis jacket and steel-toe boots. There was also a barrier set up around the perimeter of the trial pit, and we were warned of the dangers of the pit collapsing. We excavated the soil to about 4 meters deep, allowing us to get a clear insight into the types of soil available and the different depths each layer extended to. The topsoil was disregarded, as it's an organic soil which provides no use for construction purposes. The first strata was made up of a grey to brown silty clay. This strata was 0.7 meters deep, and we agreed it's most likely a fill layer due to the mixture of soils and presence of organics. The organics most likely came from alluvial deposits from previous flooding. The second strata was a grey sandy gravel with a depth of 1 metre. The third strata present was clay. There was both grey and pink clay present, extending for 1.7 metres. We agreed that the pink clay would be suitable for the construction of our dam. Although there was no water table present, there was perched water at 1.5 metres. The trial pit allowed us to practice describing the soil in order to identify it. We used the acronym MCCSSOOW to examine the soil under the following headings: moisture, colour, consistency, structure, soil type, origin, other relative information, and water table. The next step of the project is soil classification. In order to do this, we used a U38 tube to take an undisturbed soil sample to the labs in order to be tested.
Once we have taken our undisturbed sample of soil from our trial pits, we can begin to classify them by running a series of tests in the lab. For our first test, we conduct a sieve analysis test on our sample soil using mesh sizes ranging from 75 micrometers to 10 millimeters. By measuring the percentage passing at each mesh size, we can begin to draw our particle distribution curve. By drawing our particle distribution curve, we can begin to classify our soil. We can also take the percentage passing at 60, 30 and 10% to see if the soil is well graded. The Atterberg limits are the limits where the soil behaviour begins to change. These limits are the liquid limit, where the soil's behaviour changes from a plastic to a liquid state, the plastic limit, where the soil's behaviour changes from a semi-brittle behaviour to a plastic behaviour, and finally the shrinkage limit, where the soil's behaviour changes from a semi-brittle to brittle behaviour. By plotting the liquid limit against the plasticity index, we can classify our soil as silt or clay, with low, medium or high plasticity, depending on where it falls in relation to the A line on Casagrande's chart.
We carried out an investigation of the site to determine ground levels and characteristics of the area. We researched the area to ensure we would not be disturbing the habitat of any protected species. We also used GeoHive to determine that there was no karst features present on site. We found the critical flood level using reliable sources such as CFRAMS and floodmaps.ie. The critical flood level at this area for a 1 in 100 year flood was 6.46 metres above datum. We then needed to find the lowest ground level on site to find the minimum height our dam needed to be. We found this height to be 12 foot or 3.65 metres on topographymap.com. This meant that our dam had to exceed 2.8 metres to avoid overtopping. We discovered that the soil in Thomond is a sandy soil. Due to its large particle size, it would have to be compacted significantly before any construction began. Below the sandy layer is an impermeable pink clay, which will not let any water through it. In an effort to help the dam blend into its surroundings, we would sow grass seed on the Thomond side to make it more aesthetically pleasing to the people of the village.
Prior to beginning the construction of the dam, the site should be cleared of all vegetation. This may involve disturbing natural habitats, so it is important to work in accordance with the requirements of the Wildlife Act 1976. Luckily, a suitable borrow site was located behind Thomond village, so transportation costs will be relatively low during the construction process. The desired soil must be drawn in, levelled and rolled in layers to construct the dam. To optimise the compaction process, lifts or layers of 225mm should be compacted by a sheep's foot roller, rolling over the lift 6 to 12 times at speeds of 3 to 6 km per hour. On-site compaction tests include using the sand replacement test and the nuclear density gauge. These tests are more commonly used in practice than MCV and CBR tests due to the efficiency and time as a result can be obtained on-site rather than bringing samples back to the lab. 95% dry density levels must be verified by the proctograph calculated in the lab. It is important to maintain a moisture content level. If the soil is too moist, the soil must be allowed time to dry out until an optimum moisture content is reached.
Flow nets are graphical representations of the Laplace's equation and may be used to analyse seepage through the dam. It must be drawn on a scale diagram. The phreatic parabola is the first flow line drawn, which is found by drawing a directrix. Each point on the phreatic line is equidistant from the focal point to the directrix line. Length BC must be equal to 0.3 of AC. Further flow lines are drawn based off this phreatic parabola. Equal potential lines are then drawn to cross flow lines at right angles to form circular squares. The rate of seepage through the dam can be determined using this formula. In this case, it is assumed the permeability value of the dam is the same as the silty sand it lies on. The other failure modes include overtopping, boiling, sliding, and piping. The factor of safety against piping may be calculated using the flow nets drawn. We designed the filter to increase the factor of safety against piping. We used the following criteria shown. It is positioned at this point as the particles look for a release in pressure. Instead of seeping through the dam to the other side, they flow to this area. Thanks for watching, hope you enjoyed the video.